All right, welcome to The Explainer. Today we're tackling something we use every single day, but maybe don't fully understand: the brain of our computer, the CPU. We're going to break down how it goes from basically a single tiny light switch to the absolute powerhouse that runs, well, everything.
So, let's just start with this big question. Have you ever really thought about it? I mean, is your computer thinking? When you click on a link or launch an app, it seems to make decisions, right? Instantly. So how does a chunk of lifeless silicon pull off computations that feel, well, almost intelligent?
Well, the answer is surprisingly simple. It doesn't start with some super complex, grand design. Nope, it all begins with the most basic concept you can imagine: a simple on-off switch. We're talking billions and billions of them. And yeah, that number, thanks to Moore's law, has pretty much doubled every couple of years. It's just a massive army of switches working together. Okay, so what is this tiny switch? This fundamental building block is called the transistor. And look, it's no exaggeration to say this little thing is probably one of the most important inventions in all of human history. The best way to think about a transistor is just picture a water faucet. Seriously, you've got the source, which is like the main pipe where the water comes from. You've got the drain, where the water wants to go. And then, the most important part, the gate. That's the handle, the knob you turn to let the water flow or to stop it completely. Same idea with electricity.
And right here, this is the magic moment. This is how that simple switch connects the physical world of electricity to the digital world of information. When there's no voltage at the gate, the path is blocked. The faucet is off. We call that off, and we represent it with a 0. But when we apply a little bit of voltage, the gate opens, and the current flows. That's on, and we call that a 1. And that's it. That is literally it. This on-off, 1-0 state, that's the fundamental language of every single computer.
Okay, so one switch is cool, but, it's just a switch. The real magic, the mind-blowing part, happens when we start combining them. Because when you do that, you get something totally new. You get logic. So if you arrange these transistors in just the right patterns, you create these little circuits called logic gates. And now, we're not just talking about on-off anymore. These things can actually make simple decisions based on the electricity they get. The simplest one of all is the NOT gate. You can also call it an inverter. Its job is, well, incredibly simple. It just flips whatever you give it. You put in a 0, you get out a 1. You put in a 1, you get out a 0. That's all it does. Easy peasy. All right, next up, the AND gate. This one's a little pickier. It will only, and I mean only, output a 1 if both of its inputs are 1. Just think of it like saying, I want coffee and a donut. If you only get one, the condition isn't met. You need both for it to be true. Any other combo, you get a 0. And then we've got the OR gate. This one is way more laid back. It'll give you a 1 if at least one of its inputs is a 1. So, I'll have coffee or a donut. Either one is fine. As long as one of them is true, the output is true. And, just like that, look what we did. We went from a dumb physical switch to a circuit that could actually perform a logical operation. That's a huge leap. So, now we have these new building blocks, these logic gates. We can start putting them together to create even more powerful circuits. And these new circuits can do two things that are absolutely critical for any computer. They can calculate and they can remember. Let's take calculation. You can actually combine AND and OR gates to build something called an adder circuit. And yeah, it does exactly what it sounds like: basic math. It's pretty wild to think that a circuit that can literally do addition is built from just a handful of those simple switches we started with. But for memory, for that we need something a little different. And that special something is called a flip-flop. Yeah, funny name, but its job is super important. It's designed to, well, flip into one of two stable states, on or off, and then, and this is the key part, holds that state. It stays put. This is what allows it to remember one single bit of information: a 1 or a 0. Now, here's the really crucial part. A flip-flop is a clocked circuit. What does that mean? It means it doesn't just change whenever it feels like it. It's designed to change its stored data only at a very specific moment, perfectly in time with the CPU's internal clock pulse. Think of it like a metronome or an orchestra conductor, making sure every single part of the CPU is operating in perfect, synchronized harmony. This whole idea,
synchronized circuits that can hold their state, that's the foundation of all computer memory.
Okay, let's take stock. We have logic gates that can calculate. We have flip-flop circuits that can remember. We have all the pieces. Now, we can finally put them all together and assemble the brain itself, the central processing unit, the CPU.
So how do these circuits actually form a brain? Well, it really comes down to three main players working together in perfect lockstep, processing every single thing your computer does. And these three core components of any modern CPU are the control unit, the arithmetic logic unit, and the registers.
So each one has a really specific job. The control unit, that's the manager, the boss. It's not doing the math itself, but it's fetching the instructions and telling everyone else what to do. It's directing all the traffic. Then you have the arithmetic logic unit, or ALU for short. That's your calculator. It's the number cruncher that does all the math and all the logic. And finally, you have the registers. Think of these like a super fast little notepad right on the CPU's desk for holding whatever data it's working on right now.
But here's the thing. These three parts don't just sit around. They are constantly working together in this incredibly fast, continuous rhythm. It's like a dance, and it's this dance that runs every single program on your computer. We call it the instruction cycle.
And that dance is the legendary fetch-decode-execute cycle. It is the absolute fundamental process for every single instruction, kind of like the CPU's heartbeat. It goes like this. First, the control unit fetches the next instruction from memory, just like a chef grabbing the next step in a recipe. Then, it decodes that instruction to figure out what it's supposed to do. And finally, it executes the command, sending the actual work over to the ALU and the registers. And this simple three-step dance, fetch, decode, execute, it happens billions of times every single second. It's just staggering.
And there you have it. That's the entire journey. We started with one simple transistor that could only be on or off. We put them together to create logic gates that can make decisions. We built those gates into bigger circuits that could do math and remember things. And then we orchestrated all of that into a CPU, constantly performing that fetch, decode, execute dance. And that is how the physical hardware actually brings your software to life.
And when you step back, it leaves you with this really powerful idea, right? All of this immense complexity, this incredible capability, it all emerges from the absolute simplest rule possible: on or off, 1 or 0. So what does that really tell us about intelligence itself? It's definitely something to think about the next time you just click a button and watch the magic happen.